My name is James Park, and this is my lab for oscillations. Alright, so the table of contents, we have introductions and conditions, equations and key physics concepts, experiment and data, coding and explanation, analysis and summary. Okay, for the introductions and conditions. The purpose of this lab is to examine the motion of a computational spring versus in real life experiment to analyze its motion and energy. In the experiment, a spring with a mass at an equilibrium is moved by hand and let go to oscillate. Initial conditions were that there was zero velocity initially. The ball started initially at the position of this, which is negative 0.11 meters x direction, negative 0.631 meters y direction, and it started when time was equal to 0. Alright, equations and key concepts. We have Newton's second law here, F equals ma. Energy principle, which is all energy is equal to work, which is equal to potential plus kinetic. Velocity update equation, which is v final is equal to v initial plus f net divided by m, which is also equal to acceleration times t. Position update, which is the initial position plus the velocity times t equals the final position. Gravity force, which is obviously just mg, and spring force, which is 1/2 k L minus L0 to get the distance times L hat. Alright, so the experiment and data. This is the experiment I used, the given experiment right here. And using tracker data, this is the data we got. Alright, now moving on, coding explanation. So here are the initial values where the ball's mass is 0.402, position is one stated earlier, and the ball's initial velocity is also 0. And the constant and g is always equal to 9.8, as always. And the spring constant and the L0 is actually given by the video that was given earlier. And these are just fundamental equations of L hat and S, just the distance. And these are just the equations for all the energies. Over here, we put those energies earlier in a new value, so we can keep it for this part right here, where we need the new energy and the old energy to figure out delta K. Alright, and here, just negative G for the force of gravity, like we stated. Sorry, negative G times N, the mass. Alright, F of spring is just the equation, and F of net is just the additive of both of it, and this is just the velocity and position of the formula. Okay, looking at the analysis, so similarities. So the oscillation rate is almost the same. You can see that both red and blue oscillate about the same amount. However, there's a slight offset between both of them, and the magnitude also differs for y. Some possible source of error for this issue might be the air friction when the spring is moving that's not calculated in the computational model, some coding issues, and some tracker issues, like I didn't track it correctly. Alright, and this is the energy graph, and we can talk about this on the final part. Alright, what does this mean? So on the graph, the energy principle is satisfied because if you look at all the energies to add them up, they will all equal E, which is the one in the middle. So you can see how when the spring potential goes up, the gravity potential goes down, meaning that they all equal out, and this is just 0, so they all equal out. Alright, now using the data given, we tried to figure out the oscillation period. So what I did was I counted from one oscillation period to the other, so from here to here and from here to here, and I was given that for x is 1.61 seconds, for y is 1.52 seconds. My only guess to why this might be different is because the case, so the spring tension might be different, might have different stiffness between x and y, because usually we're just looking at a directly straight, like longitude one, but this only one dimensional spring pull, but in this case the spring is being pulled in 2 dimensions. They might have different stiffness. That was my lab. Thank you.